just to recall, chemistry is the study of matter. So really, it's like the most broad science. And we already learned about elements and compounds. We learned about how they react with each other. We learned about the changes they undergo. And so this unit of thermodynamics is all going to be about the energy associated with those changes. So let's recall the definition of energy. That is the ability to do work using force to move something a distance. And as you guys probably recall, we have two main types of energy that we talk about, that being kinetic and potential. So first we're going to talk about kinetic energy, and I'm sure you guys have seen it abbreviated as KE. I will do that. And so this is the energy of motion contained by anything that moves. Oops, energy of motion, not moves. And so for chem, we talk about atoms, molecules, and particles. And so how we relate them to kinetic energy is that they move faster when the temperature is increased. So we're going to relate temp to kinetic energy. And so we actually define temperature as the measurement of the average kinetic energy of particles in a system. And so another way to think about temperature being this average measurement is if you're thinking about, okay, we're going to look at a section of a highway, and of all the cars traveling down, do you think they're probably all traveling at the same speed? Let me tell you, they're not. I followed someone in this morning driving 25 in a 35. I was about to lose my mind. Anyway, so if you take all those different cars on that stretch of highway and you were to plot them, you'd get likely a bell curve where you have this initial increase, you find your average, and then a decrease. And so the average speed is where the top of this bell curve is. That lies at about 50. And so this is similar to how temperature is used as an average measurement, where, except in a room, you have trillions and trillions of molecules. And so we take an average of their movement speeds and assign them the measurement of 25 degrees Celsius, for example. And so what we're bringing back are the two different metric temperature scales. So we talked about Celsius and Kelvin in gas laws, but just to refresh, Celsius, which don't get me started on why, I don't know why America doesn't use it. I mean, it's literally based on water, the melting and boiling points of water at 0 and 100 degrees Celsius. So we have to remember then, okay, what's Kelvin then? Kelvin, so a degree in Celsius and a Kelvin, they're technically, in a sense, the same. So if you shift 1 degree Celsius, you're shifting 1 Kelvin. It's just as if the scale was reset to now say, okay, 0 Kelvin is now negative 273 degrees Celsius. And so the reason why we shifted things and we're defining this 0 Kelvin, I put the slashes through the zeros because it looks like I just wrote okay, but it's actually 0 Kelvin. So just a reminder, there is no degree associated with Kelvin. It's just Kelvin. And so 0 Kelvin, this is known as absolute zero. And the reason this is a big deal is this is what we call the temperature that all particle motion stops. And so theoretically, we can achieve it, but we got really close in 2017 on American soil. So in a lab in Boulder, Colorado, we did reach 0.00036 Kelvin using lasers. How cool is that? Okay. All right. Let's talk about potential energy. Potential energy is what kind of energy? Stored. So it's like us. We could do work if we wanted to. We're just choosing not to, right? So, I mean, you guys have heard the classic examples of a coiled spring or holding an object a certain height. But But chemistry, where we find our potential energy or our stored energy, is actually in the chemical bonds. And so this is the main spot we find it, but we also need to remember, you guys should remember this, intermolecular forces. So the attraction between molecules. So this energy is absorbed or released during both chemical and physical changes. And so we do have a way that we can measure potential energy, because you think, you're like, how can you measure stored energy? But the way we have to do so is we have to first convert it to kinetic energy. Because if you guys remember the law of conservation, that applies to energy as well. You can't just make up. So it's just a conversion from potential to kinetic. And then we measure it using a calorimeter. Calorimeter. So a calorimeter, all it is, it could be a styrofoam cup. It could be a fancy little instrument. It could be a pop can, as long as it's something that can hold a certain mass of water. Because all we do is, for example, the lab that you guys are going to be starting tomorrow is measuring how much energy is stored in a candle. And so how we measure this is how much the temperature changes, because remember, the temperature is a read of the average kinetic energy. And so joules, this is just our unit. And so they're most often used to measure potential energy. But it's the conversion of this, really. So if you burn something, you're converting that stored. If you melt something, you're converting that stored energy to kinetic. And then the last thing I wanted to talk about here is heat flow. So the nice thing with heat flow is there's a little saying here. Heat flows from where it's hot to where it's not. So, thank you. So this examples could be, for example, you guys open your front door and you can feel your air flying out of your house and the cold air coming in, or a hot pack if you have a sore muscle. It's actually the heat coming from the hot pack going into your body. Or a good chemistry example is if you're holding a test tube over a Bunsen burner, the heat from the flame flows to the test tube, which then flows to the solid. So just heat flow happens from where it's hot to where it's not.